All right, so what I want you to do right now is I want you to hit pause on the podcast here, and I want you to calculate the Ka's, and I want you to determine which one is the stronger base, which one has the stronger conjugate acid, just like we did in the previous example. All right, here come the answers for this guy. And this guy is called diethylamine. Most of your weak bases have that nitrogen in it. Really, the only reason I know they're a base is they've got a Kb. Therefore, they are both bases, and bases will accept a proton from an acid, in water in this case. So, based on the Kb's, this guy is going to be the stronger base. Between the two, to be the weaker base. Let's see, I predict then that he is going to be the stronger conjugate acid, and he is going to be the weaker conjugate acid. All right, now mathematically what you should have found is the Ka of the conjugate acid, which has a formula C5H5NH plus. If you plug that into your calculator, you'll find it to be 5.9 times 10 to the negative 6. The Ka of this conjugate acid, which has a formula of C2H5 NH2 plus, will have Ka of 7.7 times 10 to the negative 12. Now, did I predict correctly? Yes. 5.9 times 10 to the negative 6 is a larger Ka than 7.7 times 10 to the negative 12. Therefore, the pyridine, while it's the weaker base, will definitely be the stronger conjugate acid. All right. Now, ice table math is a weak acid. I know that for two reasons. Reason number one, it is not on my list of strong. About the reaction in water, it has a dual-headed arrow. You could always just draw it like this with two arrows. Okay? Also, they draw the predominant arrow larger. You'll see this sometimes. React in favor, which we already know because it's a weak acid. All right, so here's my reaction. This is going to be an ice table calculation because it is a weak acid. So initially, I have 0.50 molar. Don't care about the water. Strong acids, not strong acids. Don't care about the water. Pure liquids, pure solids do not appear in the equilibrium expression. That these are zero because they're not mentioned at all in the problem. Change in the reaction is obviously going to the right. Therefore, HF will quantity. The fluoride will gain a certain amount, and the hydronium ion will gain a certain amount. At equilibrium, then, 50 minus X is the concentration of HF, X and F is the concentration of the fluoride and the hydronium ion. My expression for particular acid is going to be the products over reactants, no water. All right, now I'm going to substitute substitute in my numerical values. So my Ka is given. My fluoride and my hydronium ions in X. Most of your, actually all, your weak acids and your weak bases will have the exact same. It's going to be the K equal to X squared over minus X. Every last one of them. There are no coefficients to worry about. They're all moving to the right, so the reactants are losing, products are gaining. They all exactly look like what I just boxed in. Solver key. Calculate X. X is your hydronium ion. And for this problem, you get 0.018 molar. That means the pH, which is the negative log of 0.018, is going to be 1.74. Just a couple of quick comments. Since my Ka is 2 sig figs, my concentration is 2 sig figs. That 0 right there is not significant. Since my concentration is 2 sig figs, my pH is 2 digits right of the decimal. Now I'm going to throw something else in. Your percent dissociation tells you how much of the original acid turns into hydronium ions. And it is calculated by the concentration of hydronium over the concentration of the acid times 100%. So here in this particular problem, my concentration of hydronium ion at equilibrium divided by the concentration initially of the acid times 100, and I get 3.6%. That means that 3.6% of the hydrofluoric acid turned into hydronium ion. This is another example. I want you to press pause. I want you to work it out on your own. I'm just going to write in the answers. Point zero pH. Now the pH, notice, is a little higher. That means there's less hydronium ion in here. And the Kas aren't that dramatically different, so it has to do with concentration. Is 3.8%. Right, now this one's different. This one is a base, but the format's going to be exactly the same. I'm going to write out the reaction because bases are a little odd. Again, you can put it two arrows, whatever is comfortable. I usually use one arrow with two heads, whatever. Bases accept. There's the conjugate acid of the ethylamine. You will notice that in this one, it's the hydroxide ion being formed. All right, so we're going to work it exactly like we did the previous examples, except for this one, it's Kb, and we're finding the hydroxide ion, not the hydrogen. So always be careful with bases. Don't care, 0, 0. It's going to have the exact same format, but instead of a Ka, I'm using Kb. My X that I'm finding is the hydroxide ion, not the hydronium. Always be careful with bases. Make sure you know which ion you're dealing with. Number one error with students. They find X, they think take the negative log of it, that's pH, and it's not. This is POH then. And then pH is 14 minus that. All right, now this one is different. This one is a completely different problem. You have to analyze the situation. Sodium acetate in water. This is a soluble salt. This is from chapter 4. So this is a chapter 4 concept. In water, this soluble salt will ionize completely. All right, so here's what happens. We have to analyze the ions because this is a 100% dissociative issue. This is a soluble salt. Soluble salts separate 100%. What you have here is a sodium ion and an acetate ion, and you have to analyze them critically. The sodium ion is technically the cation of a strong base, so he's useless. This, however, could be the conjugate base of a weak acid, so it's going to act like a base, and bases accept protons. All right, well, that's fine, but where's he going to get the proton from? Well, he's in water. Water's amphoteric. You have a secondary reaction going on here between that conjugate base and the water it's floating around in. Water's more than happy to donate. You get an equilibrium reaction where the acetate acts like a base and forms the hydroxide ion. Right? So the reaction here, or the mathematics for this, would be, that's from the salt, so you have exactly the same format as the previous two problems with one little caveat. This is acting like a base. I need a KB. Well, I don't have a KB, I have a Ka, but I can calculate a KB nice and simple. The Kb of the acetate is Kw divided by Ka, and that numerical value comes out to be 5.6 times 10 to the negative 10. It's going to be equal to x squared over 0.25 minus x. Be careful. Which ion am I solving for? I am solving for the hydroxide ion. My x is hydroxide. My x comes out to be 1.2 times 10 to the negative 5 molar. That gives me POH of 4.92 and a pH of 9.08.